all of you. I am Dr. Gaurav Saxena, Associate Professor in EC Department. So today I have discussed the Unit 1, Emerging Domain in Electronics and Communication Engineering. So the topic is BEC, BEC 101 and 201 is the subject code. So BEC 101 reflected to the first semester and the BEC 201 reflected to the second semester. So this is useful for first semester as well as the second semester students. So this is the topics we have to be described by the AKTU. First unit is to be totally dedicated to the semiconductor diode. So what is the semiconductor diode and what is the application of semiconductor diode, which have been discussed in the unit 1. And other terminal we have to be a special purpose 2-terminal diode, just like a light emitting diode, photo diode, vector diode, tunnel diode, and the LCD, which has to be discussed here. And the first topic is depletion layer and what is the VI characteristics of ideal and practical diode, and what is the diode equivalent circuit. So Zener diodes and the breakdown mechanism. So I discussed this topic. This is very important topic which has been asked in the AKTU examination. So what is the depletion layer? So before the depletion layer, so you have to be just define what is this is the textbook we have to be used in that particular to prepare this PPT. First one is the Robert L. Bolster. This is the textbook, and the H.S. Culsey and the George Kennedy, which one is useful for the unit 5 between electronics and communication system, and David Ball, because this is the electronic devices and circuit. So this is totally dedicated to the unit 3, and this is unit 1. This is totally unit 1 and unit 2. In the unit 1, we have to be discuss the what is the diode and what is the application of diode, and the other 2-terminal diodes we have to be discuss here. And the unit 2 is to be totally dedicated to the active devices, just like a transistor, field effect transistor, and the MOSFETs. So unit 1 and unit 2 is to be covered here, and partial unit 3 is to be covered here, and the unit 4 is to be covered here by using the this electronics H.S. Culsey and the Jacob Millman. We have to be use the unit 3 we have to be discuss here. And what is the David A. Ball? This one is the measurement technique we have to be discuss here, and the some others are we have to be, and other book which has to be suggested for unit 4, which is digital electronics, and this one is RP Jain. So RP Jain is the next book we have to be used in unit 4, which one is digital electronics. So unit 4 is to be totally dedicated to the digital electronics. So RP Jain is the very important book which has to be prepared that particular season. So this is the unit 1, what is the semiconductor diode and the VI characteristics of that particular diode. So we have to discuss here. So what is the semiconductor diode? So semiconductor, what is the special purpose special purpose of material whose valency or last orbit electrons is equal to 4. So we can say this is a semiconductor. So semiconductor are two types, which one is the single crystal semiconductor or compound structure semiconductor. So single crystal semiconductors are germanium and silicon, and whose valency is 4. And what is the meaning of the valency of 4? That means the last orbit electrons is 4. And the compound structure semiconductor are gallium arsenide, cadmium sulfide, gallium nitride, and gallium arsenide. So this semiconductor also known as the direct band gap material. So this is a direct band gap material, and this is a direct band gap material which is used for light emitting diode, and this one is indirect band gap material. So indirect band gap material, that means that the energy band gap and the momentum are not in the same phase. So we can say this is an indirect band gap material, germanium silicon, and the direct band gap material are which are compound material, just like a gallium arsenide. So these three semiconductors are most frequently used in the construction of the electronic devices: germanium, silicon, and gallium arsenide. So basically, the semiconductor are further we have to be divided into the two parts. First one is the intrinsic semiconductor, and the second one is extrinsic semiconductor. So intrinsic semiconductor and extrinsic semiconductor. So what is the meaning of the intrinsic semiconductor? So intrinsic semiconductor are those materials which are pure in their nature. So that means the germanium silicon is the pure in nature. So we can say this is an intrinsic semiconductor. If we doped in germanium silicon, so that particular material is called the extrinsic semiconductor. So extrinsic semiconductor are two types, just like a p-type material and the n-type material. So the what is the history of that particular diode? So simple semiconductor application is p-n junction diode. So diode is to be discovered in the 1939, was using germanium diode we have to be discovered, and the transistor is to be discovered in 1947, which is using by germanium. But in 1954 silicon was used in transistor because silica is less less resistivity. So silicon is temperature sensitive, less temperature sensitive, and the abundantly available. So we use the silicon because germanium is very not much in the nature. So we use the silicon, and which is germanium is very temperature sensitive material. So we use a silicon with respect to the germanium. High speed transistor, so if we use a gallium arsenide or direct band gap material, which has to be first introduced in 1970, so high speed transistor we have to be introduced in by using the compound material, semiconductor material, just like a gallium arsenide. Silicon, germanium, and gallium arsenide is the semiconductor of choice. So we use, if we use a temperature sensitive device, so we use a germanium. If we want to design a temperature insensitive device, so we use a silicon, and silicon is very less temperature sensitive, and which is available in the nature frequently. And if we use a gallium arsenide, so the gallium arsenide is a compound material whose mu, what is the mu is the what is that means the mobility of gallium arsenide is much higher than the germanium silicon. So we use gallium arsenide component in high speed switching purpose. So this is the atom structure of germanium or silicon. So we see that, so this is a 32 germanium. The last orbit electrons, you have to see that this is 1, 2, 3, 4. So what is the 2, 8, 18, and 4? So this is the configuration of germanium. So in that particular system, you have to see that the 4 valency of that particular electron. So that means outermost orbit, 4 free electrons or valence electrons to be here. So we can say this is a intrinsic semiconductor, single crystal semiconductor. Or this is called a germanium, and this is silicon. So the silicon is 14. So what is the structures? 2, 8, 4. So that means in the outermost orbit is the 4, and you have to see this, the binding energy of that particular electrons from this one is less, but the binding energy of this electrons is to be large. So that means if we migrate from valence band to conduction band, so high electric field is to be here, we have to be applied, then they migrate from the valence band to the conduction band. So if this is the gallium and this is the arsenic, so this is the simple structure of the covalent bonding of silicon. So we have to see that silicon having a outermost orbit of 4 electron. So this is a intrinsic semiconductor. This is a pure semiconductor of silicon. So they bond, covalent bond, you have to be here is another sharing that particular bond. So this is a silicon covalent bonding we have to be share here. So if this is a gallium arsenide. So gallium arsenide having a 5, 1, 2, 3, 4, 5. So they bond with gallium having a 3 electrons in the outermost orbit. So they completed the 8 electrons in the orbit. So this is the intrinsic semiconductor of multi crystals, di-crystals semiconductors. So what is the meaning of the energy band gap? So the valence band and the conduction band. So the energy level between the valence band to the conduction band is called the energy gap. So in the insulator, we have to see that the valence band and the conduction band having a greater than 5 electron volt energy band gap, but in the semiconductor, which one is 0.67 for germanium and 1.1 electron volt for silicon and 1.43 electron volt as gallium arsenide. But in the conductor, the valence band and the conduction band which are merging from each other, so we can differentiate these conductors, semiconductors, and insulator by using the energy band diagram. So, so N type and the P type material. So we can earlier we have to be discussed here. So the material are two types, and that's intrinsic semiconductor and the extrinsic semiconductors. So extrinsic semiconductor we have to be further divided into the two parts: N type materials and the P type materials. So the N type materials are created by the adding element with 5 valence electrons, such as antimony, arsenic, and the phosphorus. So if we introduce a antimony, arsenic, phosphorus in germanium or silicon, so they produce a extra electrons. So the electrons charge carriers to be here. So the electrons, we have 4 electrons is to be pair here. This is the antimony. So 1 electron is to be vacant. So they produce a more electrons. So in the intrinsic semiconductor, if we doping having a 5 valent electrons, so they produce a electron, so they create a high electrons mobility carriers. So we can say such type of material is called a n-type material. So in the n-type material, the electrons are majority carriers and the holes are minority carriers. So antimony, arsenic, phosphorus, we have to be introduced for making a n-type material. So this is also called a donor atoms. So they produce a electron, so we can say this is a donor atom. So and p-type material is also called a acceptor atoms. So if we introduce a trivalent impurity, we have to be introduced just like a aluminium. So aluminium having a 3 valency, so we if we introduce a aluminium, so they convert a 3 valence electrons, and 1 electron is to be vacant, so they produce a holes. So in the p-type materials, we have to be added a 3 valence electrons, and the majority carriers are holes in p-type materials. So such material is called the p-type material. Um, this is the uh, table, Mendeleev tables. So we have to be see that phosphorus having a 5 valency, antimony is arsenic, bismuth. So we use a 5 valence electron, and so that is a so I already discussed here. So the first application of the semiconductor diodes is semiconductor physics is PN junction diode. So what is the meaning of PN junction? So PN junction. So we introduce a extrinsic semiconductor, and we divided into the two parts. This is P type and N type. So in this we have to be doped P type material, and this portion is to be doped N type material. So such material is called the PN junction diode. In P type diodes, we have to be introduce a holes is the majority carriers. So this is a holes of majority carriers, and the electrons are minority carrier. But in the n-type material, electrons are majority carriers and holes are minority carriers. So that means what is the meaning of the minority and majority carriers? So we introduce, if we know biasing is to be placed here, so that means the open circuit. So we at the room temperature, so some of the covalent bond is to be break. So that means some electrons is to be transferred here, n type to p type, and some holes is to be transferred here to n p type to n type. So here, so and this is a depletion layer which has to be enhance the what is the electric field from immobile signs. So in n types, the positive ions here, and p type is negative ions here. So the internal electric field is to be here from positive to negative. So we can say this is the internal electric field which have to be applied, which oppose the which oppose the migrate from holes from P to N and electrons from N to E. So this is the barrier potential. So by using the barrier potential, a depletion width is to be created. In the depletion width, we have to see that no mobile signs to be here. So that means the depletion layer is the layer, and in the PN junction diode, so in that no mobile signs is here. So that particular width is called the depletion width. If we increase the reverse bias, so the depletion width is to be increases, and we increase the forward bias, so the depletion width is to be reduced. So what is the meaning of the forward bias and the reverse bias in the PN junction diode? If we put P type material to the positive terminal and N type materials to be negative terminal, so such circuit is called the forward bias condition. So in that particular medium, the P type is to be connected to the positive terminal, N type is to be connected to the negative terminal. So such element is called the forward bias condition. In that particular condition, this is plus. So that means this terminal is to be plus. That means holes having a positive charge. So they reflect here and going to the N type, and here this is the negative terminal, and so electrons are reflect here and repel here, and they have to be migrated from the N side to the P side. So because the holes is to be flow from P to N, and current is to be flow from in that particular circuit from P to N. So this current is called the diode current. So in that particular reason, so they flow the electrons easily from N to P, and the holes is to be flowing from the P to N. So the depletion width is to be reduces. In that particular region, the depletion width is to be very much less, and the diode resistance is also less. But if we apply a that means if we apply a reverse bias condition, so P is to be connected to the negative and is to be connected to the positive. So the holes is to be positive charge. So this one is negative charge. So they attract the holes. So holes are to be um, accumulated in that particular region. So no holes is to be present here, and no electrons is to be present here. And because the if we apply a plus charge, so electrons also accumulated here. So from this to this. So this is the immobile region. So this immobile region is also called a depletion region. So in that particular purpose, in the reverse bias, depletion region is very high. If we increase the this voltage, so the depletion width is to be increases. So in such a condition, that means if we increases further, so the breakdown is occurs. So that particular voltage is called the PIV. If we increase the reverse bias voltage, at that particular voltage, if we further increases, the diode becomes breakdown. So that particular voltage is called the peak inverse voltage of that particular diode. So this one is to be here. So next is, what is the ideal characteristics of diode? So before this, we have to be just forward a what is the meaning of characteristics. So characteristics to be defined by IV characteristics of the diode. So what is the diode voltage we have to be applied here across the diode, and how much current is to be flowing. So that particular that particular graph is called the VI characteristic or IV characteristic of the diode. So in the practical purpose, so the diode resisting the forward bias condition is to be here. So if the diode, PN junction diode is forward bias, this is forward bias. So that means P is to be connected to the positive of the terminal and N is to be connected to the negative of the terminal. So such circuit is called the forward bias condition. So if we choose a germanium or silicon, so germanium having a cut-in voltage, or what is the threshold cut-in voltage, knee voltage, or knee voltage is 0.3 volt, and the silicon is knee voltage is 0.7 volt. So what is the meaning of this knee voltage? So if we for conducting that particular diode, so we apply a greater than that particular voltage. That means if we apply a greater than 0.3 volt for germanium, then the current flow gradually. But in the case of silicon, this should be 0.7 due to this material composition. So this is forward bias. In the reverse bias condition, we have to be already discussed here. Okay, but in the reverse bias condition, some of the minority carriers to be transmitted from P to N and N to P. So some leakage current flow in that particular circuit during the reverse bias condition. So there, that is called the reverse current. So in the reverse bias region, what is the meaning of reverse bias? So reverse bias region, if P is connected to the negative of the terminal and N is to be connected to the positive of the terminal, so we can say this is a reverse bias condition. In the reverse bias condition, you have to see that if we increase the volt reverse bias, so no current flow, or we can say this is very few current flow. So the value of that particular forward current in the range of milliampere, but in the case of reverse bias, this one is microampere or nanoampere for germanium and silicon. So but we increase the voltage, so a heavy current is flow, so this particular voltage is called the reverse breakdown voltage. So reverse breakdown voltage to be RB. So what is the reverse breakdown voltage? If we increase the reverse bias of across the PN junction, so a heavy current, so we can say this is heavy current is flowing. So that particular voltage where the current is gradually increasing in reverse bias, so we can say this particular voltage is called the reverse bias. So this is the practical characteristics of the PN junction diode. But in the case of ideal diode, so what is the meaning of ideal diode? So this is a practical consideration of the diode for germanium and silicon. This particular voltage is 0.3 and 0.7, and this is the diode resistance. For forward bias, this diode resistance is ideally 0, but in the case of reverse bias, this diode resistance should be infinity. So if we draw it for what is the condition of ideal diode? Condition of ideal diode is the breakdown voltage should be 0 volt in forward bias, and diode resistance should be 0 ohm. That means what is the meaning of diode resistance is 0 ohm? This one is short circuit. So if the diode is short circuit, or we can say if we draw a VI characteristics of ideal diode, so the cutting voltage is 0. So that means at the 0 volt, the diode should be starting conducting, and the diode resistance is 0 ohm. That means current is infinity. So ID is infinity and the RD is 0 ohm. But in the reverse bias condition, what is the reverse bias condition? In the RD is infinite. So that means no minority carriers to be produces the current. So that means the value of current should be 0 in reverse bias. So that means this is voltage, diode voltage. So this is the forward bias voltage and this is reverse bias voltage. So in that particular case, diode should be open circuit. This is reverse bias. This is forward bias. So which has been forward bias and reverse bias, we have to be included by using the battery. We have to be just see that the P type terminal is to be connected to the positive, N type connected to the negative. So we can say that this is holes to be migrated from P to N and electrons to be migrated from N to P. So the current is flowing in the direction of the holes flow. So this is the practical characteristics. So I just introduced what is the gallium arsenide diode. Cut-in voltage is 1.2 volt, and the silicon diode is 0.7 volt, and the semiconductor germanium diode is 0.3 volt. So what is the temperature effect on the VI characteristics? If we increase the temperature, so the cut-in voltage to be reduces. So what is the meaning of this? So effect of temperature on VI characteristics. So if we increase the voltage, so what is this is diode voltage and this is the diode current in milliampere. So at 27 degrees centigrade, this characteristic follows. This is a germanium diode, or this is the cut-in voltage 0.3 volt. If we increase the temperature, what is the temperature? So if this is 37 degrees centigrade, the cut-in voltage to be reduced. So how much cut-in voltage to be reduced? So this is dV by dt is equal to minus 2.5 millivolt per degree centigrade. So that means if we increase the temperature for covalent bond breaking process to be fast, that means the 2.5 millivolt cut-in voltage to be meeting at previously, or that means the negative of, that means if I can say, if we increase the 10 degrees temperature, so what is the reduction in cut-in voltage? Which one is, if we multiply this to minus 25 millivolt per degree centigrade. So actual cut-in voltage at 27-degree temperature, which one is 0.3 volts. So in 37-degree centigrade, so the fast breaking, so that means this one is 0.3 minus 25 millivolt. So this is the new cut-in voltage of that particular diode. So this is the temperature effect on VI characteristics in forward bias condition. So I already discussed the piecewise linear model. This is the piecewise linear model. Here the cut-in voltage we have to be introduced. This is a silicon, so the cut-in voltage is 0.7 volt, and the diode resistance in forward bias condition is very few, and that means the 0 ohm in ideal case, but in the practical case this one is 10 ohm. So we easily draw this. This is the 10 upon 1. So that means this current is to be flowing. So if we draw a find the what is the average resistance of that particular diode. But this is a simplified model. That means that if we not introduce the 10 ohm resistance, because this 10 ohm resistance with comparison to the load resistance, which is high, very much high, that means that in the range of kilo ohm. So we not taking that particular low resistance for in the calculation. So this is a simplified model. So in the simplified model, we have to be taking in a cut-in voltage 0.7 volt, but resistance is to be replaced because that particular reason, which is very much less than the with comparison to the load resistance. So we see that the resistance is should be 0. So that means the M is equal to tan theta, which is equal to tan 90. So tan 90 is infinity. So M is the y over x. So ID upon VD is equal to infinity. So what is the VD upon ID is equal to 0. So VD upon ID is the resistance. So in this case, in a simplified model, so the M is equal to tan theta. So that means the slope is VD to ID is 90 degree. In this case, the resistance should be 0. So we can say if we neglect the resistance, so the slope is 90 degree and the cut-in voltage is 0.7. So that means this is slope is 0.7. But in the reverse bias condition, you see that this is 0 volt. So this is the ideal approximation. So I already discussed this is ideal characteristic. This is forward bias condition. This is reverse bias condition. So we have to be discussed here. This is a piecewise linear model. This is linear model, and this is the IV characteristic. This is the simplified network. This is the IV characteristic. This is the ideal device. This is the ideal characteristics of that particular diode. So what is the meaning of, what is the application of IV characteristics in PN junction diode? So we extract the value of the static and dynamic resistance of that particular diode by using the IV characteristics. So what is the static resistance? The static resistance at that particular point, if the diode is conducting, what is the what resistance is to be appear across the diode? So we easily calculate VD upon ID. So this is the static resistance at particular point. And if we find the AC resistance, so AC resistance we have to be introduced by using the formula 26 millivolt. This is the threshold voltage, which is calculated by KT upon Q upon ID plus RB. RB is going the 0.1 ohm, which is higher for 2 ohm for low power devices. So we easily calculate the static and dynamic resistance by using the IV characteristics. This is the average AC resistance. So how we calculate the average AC resistance? So in that particular path A to B, so this is the final voltage, this is the final initial voltage. So final voltage minus initial voltage upon final current upon initial current, so delta VD upon delta ID. By using this formula, we have to be calculate the what is the average AC resistance in that particular path.